Okay, welcome to this first video as we go ahead and get started on our venture into probability and statistics. And before we actually dive into what we're going to be talking about in this video in sections 2.1 and 2.2 that relate to our textbook, I want to just sort of get things started by doing a sort of brief kind of overview of thinking about what we're going to get ourselves into, talking about probability and statistics and how those are different and related. Probability versus statistics here. Okay? Probability versus statistics. Are they different? It's not uncommon for us to really have a hard time to put that into words. What's the difference between probability and what is the difference between statistics? I'll start off by saying that elements in probability allow us to draw conclusions about characteristics. Allow us to draw conclusions about characteristics of hypothetical data taken from the population. Conclusions about characteristics of hypothetical data taken from the population based on known features of the population. Known features of the population. Population. There we go. Based on known features of the population. A common thing that we'll do throughout this is talk about like the idea or experiment of flipping maybe a fair coin, say a handful of times. Like say you were going to flip a fair coin 5, 6, 7, 8 times, right? And then you can talk about elements of probability and say how likely is it that when you flip that coin 5 times that you get 4 heads in a row, right? 4 out of the 5 flips being heads. And you can come up with that number, and that's a probability question, right? But that's based on knowing that it's a fair coin. It's based on knowing, theoretically, there's a 50-50 chance of getting a head or tails. And without knowing that detail, you wouldn't be able to talk about that probability, okay? So what can we say about statistics then? Statistics are really all about getting some inferential ideas. Using statistical inference on a sample. Let's try that again. Inference on a sample. Using statistical inference on a sample allows us to draw conclusions about the population. Allows us to draw conclusions about the population. Without knowing the actual parameters of the population. Without knowing the actual parameters of the population. So we can use statistical inference. So we can take a sample of a population and then we can maybe come up with some conclusions, but we don't actually need to know the details of the actual population, right? A common statistical thing, specifically on election years, right, would be, taking a sample of voters and seeing, who is currently in the lead in before the actual election comes, right? You take a sample of voters, you survey the voters who you're going to vote for, and then you can say, well, there's a 63% chance candidate A is going to win the election based on the sample. But you don't know all of the parameters. You don't know all of the details of the population, right? We didn't survey every single member of the population, so we don't know that, but we are inferring. We usually start at a sample, we'll make an inference on a larger body there, right? And so there's some interplay here, right? There's interplay between this. There's interplay between this. So we have a population, and if we know things about the population, then we can use probability and talk about the likelihood of getting a sample from that population that meets specific characteristics. Whereas if we start with the sample, we can look at the sample and use statistical inference or statistics to talk about what we think is true about the population. Statistical inference. There's this interplay here. The bulk of the first chunk of this course is going to be about probability. And then once we have a good handle on that, the last third or so is going to be about statistical inference and talking about statistics. Okay, so just a little bit of an introduction, just to foreshadow a little bit of kind of where we're headed. We're going to be talking significantly about probability as we move forward here right off the bat. Okay, so I'm going to leave that as is for now, and I'm going to go ahead and get started. What we really want to start with is section 2.1 right now, talking about sample space. Sample space is what we're going to do. We're going to talk about sample space here. Okay, in section 2.1, we're going to have a handful of, relatively basic definitions and terminology. Not too exciting stuff at the start, but we do need to be all on the same page with our terminology here. So some of what we need to do is just become familiar with this. All right, let's go ahead and define what an experiment is. An experiment is a process. An experiment is a process whose outcomes cannot be predicted with certainty. Whose outcomes cannot be predicted with complete certainty. Predicted with certainty. The sample space, we usually will denote this capital S. Sometimes write a little vertical line on my S's like that, so it doesn't look like a 5, that we know that's a capital S there. The sample space, capital S, of an experiment is the set of all possible outcomes of an experiment is the set of all possible outcomes. All right, let's take a look at an example. Let's say we will roll, let's try that again. Let's just roll a standard die one time. Roll a standard 6-sided die one time. Let's write out the sample space here. Capital S, the sample space, set of all possible outcomes. So we have our set notation, our squirrely brackets. If it's a standard 6-sided die, we can identify the face that is showing at the top after we roll it by counting the number of dots, numbered 1 through 6. And that would be the sample space of rolling a 6-sided die. Those are the possible outcomes that we can get when we roll a standard 6-sided die. Each individual outcome now is called a member or a sample point. Each individual outcome is called a member or a sample point. It's called a member or a sample point or an element. Or an element of the sample space. Of the sample space. Let's take a look at a couple more examples here real quick. Consider the set of all points x comma y on the boundary or the interior of the circle. Boundary or the interior of the circle with radius equal to 2, r equals 2, that's short for radius, centered at the origin. Centered at the origin. What is the sample space of all, how can we write the sample space of all possible points here? This is a little bit more tricky to do because the sample space here is infinite. So I can't just list out all the ordered pairs. There's nothing here that says these points have to be integers or anything like that. So we're going to have to do this in a more sophisticated notation. And we're going to go ahead and write this in set builder notation. So we'll say the S, the sample space, is the set of all ordered pairs x and y. We can use a vertical bar. That stands for such that. All ordered pairs x and y such that. And we need it to be on the boundary or the interior of a circle with radius 2. Think to yourself, do you remember how to write the equation or inequality of a circle with radius 2? It should be x squared plus y squared. Circle with radius 2 on the boundary or interior, so we can be less than or equal to 4. Less than or equal to 4. Let's try another one. B. How about the number of students, let's say, attending a virtual class meeting of Stat 3611, just to get a feel for writing this set builder notation, okay? So here's what we can do. This is going to be the set then. So what is our potential elements? These are just numbers. It's a number of students. So we want x, set of all x, where x will be a number such that. Now the number of students, x has to be an integer. We're not having half students, hopefully attend virtual class sessions. So we can either write that out. You can say x is an integer. And then we can list a comma if we have more things. We can use our proper math notation where x is an element of the integers. Looks something like that. With our fancy capital Z, that just means it's an integer. You might have seen real numbers look something like this. Whole numbers, I think, look something like that. Yada, yada, yada. Z is for integers. Or just write it out in, full words. X is an integer. And then that's going to be having a lower bound of 0. And our upper bound, whatever that is, let's say theoretically that could go to infinity. If there's an upper limit, if there's only 50 people in the class, then maybe x just goes from, 0 to 50. This is not really well specified, but it's just a little bit of practice on writing it out in set builder notation, okay? Good. So there we go. So there's some practice writing out sets, looking at that a little bit. Now, there's one other thing that we want to talk about in terms of sample space, and that's sort of an organized way of listing potential elements and visualizing them and making sure you don't miss anything. And we're going to, of course, talk about a tree diagram. We're going to talk about a tree diagram. Some of you may know what a tree diagram already is. It's very useful for a variety of things, and we'll start with it here on the first day, and this is going to potentially be used throughout the semester, even for more advanced probability questions. So in this tree diagram example, let's say that we are going to be listing 3 items. Let's say we have 3 items that are selected at random. Each item is inspected and classified. Each item is inspected and classified as defective. There's my pen here. Should get this back. Hello. Oh. We're off to a good start. Potential low battery on the stylus. Let's see here. Classified as defective or non-defective is really all we're looking for. There we go, and we're back. Okay. Classified as defective. So I'll just call capital D for defective or non-defective. I'll call it capital N, short for non-defective. All right, and we want to make sure we can list out or count all the possible ways that we could select these 3 items, whether they're defective or non-defective. And so when you have something that's something that can be thought of as a sequential process, tree diagrams can be very useful. So let's take a look at the possibilities for the first item. Right, the first item, I'm going to try to give ourselves some space here. We select it, and it's either defective or non-defective. All right. Then you've got your second item that you choose. And that one is either defective or non-defective. And so we'll extend another branch from each of these possibilities. So we could say, well, that one could be defective or non-defective from there. And in this case, we could have defective or non-defective. And lastly, we have the third item. So we can extend a branch from each of these 4 possibilities now. So we can go defective or non-defective there. We can go defective or non-defective here. Defective or non-defective here. So on and so forth. And if you had 4 items, 5 items, right, you could continue in this fashion. And this would be nice because now we can make sure that if we wanted to list all these out, we're not missing any potential sample points, right? And so what is the possible sample point? Well, follow a branch all the way through, and that's an associated item. So this first branch would just be the sample point D, D, D. That's just getting 3 defective items, right? Then we could have D, D, N, D, D, N. So if we have D, then maybe we go along N here. So D, N, D would be another one. D, N, D. Then we have D, N, N. D, N, N. That looks good. And then now we're going to the bottom branch. Then we have N, D, D. N, D, D. There we go. N, D, D. Then we have NDN, NDN, NND, and the last one, of course, is NNN. NNN. And this is a way to make sure we can, if we're trying to list them, we can list all of them without making sure that we're missing any in between. Of course, if you just want to count the number of sample points, we just go to this third branch here and just say 1, 2, 3, 4, 5, 6, 7. There's 8 of them. But if you want to list out what they are, this is a good organized way to do so.